we'll make your weekend like fabulous. We'll make it uplifting. Your red pen won't even touch those. Your red pen won't even touch those things, other than to write the $100.
No, we should get stickers on the foot.
Yeah, we'll bring our own stickers and put our own stickers on the list, so you don't even have to do that.
Okay. Questions for today on aromaticity, anti-aromaticity, non-aromatic. Aaron? Anti? What do you want to know about it? Kyle? Okay. So, first things first. All right, let's look at a couple of these. So, first thing is aromaticity means that molecule has some sort of superstability, is what aromaticity would mean. So if a molecule was anti-aromatic, that means that it would be super unstable and actually not form. Non-aromatic is kind of in between. So what we have to do when we look at these is we have to take into account the fact that a molecule will not willingly become super unstable if it can do anything about it. Okay. For instance, if I take this cyclopropene and I make it a carbocation, our two criteria for something to be aromatic are what? All sp2 atoms in the ring, which causes the ring to become planar. And then, what's the second rule? 4n plus 2 numbers of pi electrons. Okay. Now, usually that 4n plus 2 causes people issues. So are we all okay with that?
It's just a minimum of 4n plus 2, right?
No, it's 4n plus 2, where n is a number of is an integer. So Kyle, n is an integer from 0 to, it's just an integer value, 0, 1, 2, 3, 4, 5. So here's what 4n plus 2 really means. I could memorize all of the possible numbers of pi electrons that would give me aromaticity. Okay. It turns out that they are 2, 6, 10, 14, 18, etc. And those numbers make up the mathematical series 4n plus 2, where n is equal to 0, 1, 2, 3, etc. So when the theoretical concepts were developed, they stuck to the formula so that you could generate the numbers at any time. So that's what n is. N is an integer that will generate the series of electrons that will allow a molecule to be aromatic.
And are these rules absolute? Are there any case where I would have, the right pi electrons for the aromatic stability, but it wouldn't have another factor?
Yes.
But it would still be aromatic?
No.
Okay.
It's got to have both.
Okay.
It's got to fit both. So we'll go through a number of examples, but it's got to fit both. Okay. All the carbons or all the ring atoms have to be planar, which makes the ring planar, and it has to have 4n plus 2 number of pi electrons. Okay. So that means 4 pi electrons not allowed. 8, not allowed. 9, not allowed. Actually, none. There's no odd number of electrons that are allowed. It all has to be even. So that's what the 4n plus 2 rule means. And it has other consequences, but that's beyond the scope of this course again. Okay. So if I go to this cyclopropenyl carbocation, how many, first of all, are all the atoms sp2? Yes. How many pi electrons? 2. So that molecule would then be aromatic. It would have stability that would be far more than what you would expect. If I'm going to define what superstability means, it means that it's more stable than what you would normally expect. Normally expect of what? Of an allylic carbocation.
So technically, could we just count the pi electrons and determine from there? Like, basically not have to go any further after that?
No. No, you got to do both. You have to look at both. So, for instance, here's one. The one all the way to the right. Aromatic or not? No, but it has 6 pi electrons. See, you wanted to just stop at 6 pi electrons? That's not going to work. So in this case, we got 6 pi electrons, but what? But this atom is sp3 because it's sp3. What do I do if I want to make that aromatic? I could make it a carbocation. So I could say now, if I make that a carbocation, is it aromatic? And the answer is yes. And that's the tropylium ion that was, I think, in your online quiz. If I put a negative charge, well, let's deal with the negative charge in a couple minutes. Okay, because if I put a negative charge there, we got to really think hard about what happens. Right? But if I put a positive charge there, all of the atoms are sp2 hybridized, and I've got 6 pi electrons. That would be aromatic. The alkane wouldn't be, and we'll deal with the anion in a minute. So 4n plus 2, with all the atoms being planar, is aromatic. What is anti? So this is aromatic. What's anti-aromatic? Having all of the atoms planar and only 4n numbers of electrons. Now, the first thing that we need to deal with anti-aromaticity is that the molecule is going to avoid this situation if it can. Well, you could say, how's it going to avoid that situation? Well, carbons, if I have a carbon that has 3 bonds and an unhybridized P, that carbon has a choice, actually. It could be sp2, and it actually is always sp2 if there's a plus charge on it. But if it has a pair of electrons, it has a choice. It can either go sp2, or it can decide to go sp3 by putting its lone pair into an sp3 hybridized orbital. So an sp2 hybridized carbon can go back and forth, as can a nitrogen or an oxygen, which I was in the video. Right? So when you have a lone pair, and in carbon's case, when it has a lone pair, it's a negative charge, it can make a choice. It can do sp2, it can do sp3. Okay. Yeah.
I know I have a different question. Something else about you.
I'm on a roll.
Yeah,
I'll come back to it. I'll come back to it in a minute. Okay, does that make sense to everybody that the carbon can either go sp2 or sp3? So let me come back to my cyclopropene group, and now let me go ahead and put a lone pair there so that now there's a negative charge. And this one was in the online quiz. Might have caused some debate, apparently. People were arguing back and forth. Or not. It's an online quiz. No sense in, burning friendships over that. Unless that's a normal, characteristic of your friendship. But that's another class. So if I make this now a negative charge, the carbon has two choices, right? It can become sp2, and becoming sp2, what that means is the double bond already has its p orbitals. The carbon could say, okay, I'm going to put its 2 electrons in a parallel p orbital. Now I've got 4 electrons, and the system would become anti-aromatic. And that means that molecule would be really unstable. But it's got a choice, right? It can say, you know what, I don't want to be that unstable. Instead, what I'll do is I'll make myself sp3 hybridized and put a lone pair in an sp3 hybrid orbital. And now there's no continuous parallel p orbital system. Because what we're really talking about when the molecule has all sp2s and it's planar is that all those p orbitals become a continuous system. So if an atom breaks that, it's not aromatic. You'd say, okay, it's a triangle. Right? Triangle has to be planar because 3 points define a plane. That molecule can't get out of it, but it could say, I'm just going to become sp3, and then I'm not going to be really unstable. I'm just going to be less unstable. So the molecule isn't going to choose to become anti-aromatic unless it has no choice. And for carbon, what that means is it can go sp3 instead of becoming sp2.
So if it becomes sp3, that would just be a non-aromatic compound?
Yes. It would be non-aromatic, which means it's not going to be super stable, but on the other hand, it's not going to be super unstable. Does everybody kind of see where I'm going with that? Vinny? It could do the same thing, depending on its hybridization. So if it has a choice between sp2 and sp3, if it chooses sp2, that pair of electrons got to become part of the system. If that leads to it being aromatic, it's going to do that. If that leads to it becoming 4n, an anti-aromatic, it's not going to do that. It's just going to stay sp3.
Besides carbon, though, how do you know if it's going to choose sp2 or
By looking at the Vesper rules. So in other words, anytime you have 3 bonds and you've got the possibility of 2 lone pairs, those 2 lone pairs can become a P. They can orient themselves to become a P.
So in this scenario, it didn't have a choice, so it remained it needed sp2?
No, it still has the opportunity to become sp3. What it doesn't have the opportunity to do is not become planar. Because this is locked in planar. But we have to move a little bit past the planarity and understand that, yes, all the ring atoms have to be planar, but what makes them planar? They're all sp2, and all of the p orbitals then get lined up to make that continuous continuous pi bond. So that means in the quiz you'll get credit either way when I go back and grade it. If you said anti, that's fine. If you said non, that's fine. If you said it was aromatic, that's not fine.
But technically it's non-aromatic.
Technically it's not aromatic because it's going to be less. It's not going to choose to be the most unstable it can be. Molecules go to their most stable. Okay.
What would be an example of something that would choose to be sp2 rather than sp3?
It can't. You don't have something that would be this one. Well, this one's already forced there. Let's say I put a negative charge here. Let's say I take the cyclopentadiene. Cyclopentadiene by itself would not be aromatic because it's got the sp2. It's got the sp3 hybridized carbon. If I take away a proton and make it a negative charge, what happens to it? Now it's got a choice. So the 5-membered ring, these 4 are already sp2. Now it's up to that carbon to decide. In this case, if it decides to go sp2, it has a lone pair to add to the system. So here I had 2 pi electrons. Here I have 2 pi electrons. If it contributes its 2 pi electrons, I now have a grand total of 6, which is what it needs to become aromatic. So that's an example where it would choose to become aromatic because it's going to choose to be super stable. And again, I'm giving this a choice, right? But it doesn't have any choice. Molecules will always go to their lowest energy. So in this case, their lowest energy is becoming aromatic. Same thing, I think this is the same thing, right? If I looked at this molecule, it's got 2, 4, 6, 8, but that CH2 is not sp2, so the alkane would not be aromatic. But if I took away an H plus and made that carbon negative, what would happen? Well, if it decides to go sp2, all the atoms are sp2, and it would now contribute its 2 electrons in the pi system to then become part of the 2, 4, 6, 8, 10. So then I would get 10 pi electrons here in that system, so that anion would become aromatic. The carbocation wouldn't be. The carbocation would actually be 2, 4, 6, 8. It would be anti-aromatic. Which means that that carbocation would actually not be very stable. I don't know. Let's see if we're ready to move on. Does that kind of make sense to everybody? So the reason I gave all these alkanes is because I can turn many of them into anions or cations that then will or won't be aromatic. Now, sp2s just regular carbocations, they have no choice but to be sp2. I'm sure there's probably a really bizarre example out there, although not that many, where you could have an sp2 hybrid, where you could have a non-sp2 hybridized carbocation. But I think that's not the case. But sp3, like I said, sp3 can choose. If it's a negative charge or if it's got lone pairs, it can choose. Sarah?
So, for example, with that, the triangle with the anion, if the electrons were to act as sp2, then you would count the electrons as 2 pi electrons, but if they act as sp3, they're included in the...
They're not included. So if they're sp3, because the sp3 orbital isn't perfectly parallel to the other p orbitals, then it doesn't count as part of that system.
So then those would act as basic?
They would just be basic, yes. Yes. It would just be a C minus.
Okay.
I'm sorry, you know that tritonium cation?
Yes.
Did you say that is an aromatic? Or
Yes, it is aromatic.
Because it has 6 pi electrons
Yes.
total. Okay.
Yes. So all the atoms are sp2 hybridized, even though it's contributing an empty p orbital. That empty p orbital is part of the whole system. So those 6 electrons are basically moving around that whole system. I mean, that is the structural characteristic of aromaticity, that you've got parallel p orbitals, and those p orbitals all contain the electrons. 4n plus 2 numbers of electrons. Right. So we're okay with that? Yes, no? Okay. Lisa, what's your question?
Just could you go over the basicity of the last 4 verses for the last slide we covered.
These. Okay. So we already know a C minus is basic, right? And for some reason we don't say whether the carbon is basic or not, because if it's C minus, it's basic. But these are all, the difference there is a C minus is basic because it's a C minus. It wants to get the neutral and pick up a proton. All of these examples are not. They're neutral. And so, like, we know that NH3 is a base because it will pick up a proton to form NH4+. We already know that an O with its lone pairs can pick up a H+, and that's how we make oxonium and H3O+. So when we look at heterocyclic molecules with nitrogen or oxygen as part of these rings, the question becomes, are they basic? And they can only be basic if they have lone pairs that are not part of an aromatic system. So looking at the second one, which is pyrrole, in the pyrrole system you have already a conjugated diene. So I've got 4 pi electrons. The nitrogen is in a position like the carbon was in. It says, okay, I've got a lone pair. I can go either sp3 or sp2. If I go sp3, the lone pair is out of the pi system, and the molecule's not aromatic. But then it says, but if I become sp2, my lone pair becomes part of a parallel p orbital that now becomes part of the pi system. And now instead of the pi system having 4 pi electrons, it now will pick up my 2, and as a molecule, I will become aromatic and I will become superstable. And so that's what the molecule does. The nitrogen decides in pyrrole here, it decides, okay, I'm going to become part of the pi system, but now those electrons are tied up as part of that pi system. So they can't be used to bond an H+. If the pair of electrons was outside of that pi system, they could be used to bond an H+. So even if you had an H+ around, those electrons can't bind it. And so that nitrogen would not be basic. So that nitrogen would, that's not a basic nitrogen. On the other hand, the molecule above pyridine is a very strong base. And the difference here is actually the hybridization of the nitrogen. This nitrogen has no choice. It is sp2. So it's already its pair of electrons is already part of the pi system because that nitrogen is double bonded to a carbon. So the pair of electrons that is in the pi system is not available to bond the H+. But the nitrogen isn't bound to a hydrogen. Instead, it's got a lone pair. And that lone pair now is outside the system, and it can pick up an H+ with ease. So that nitrogen, because it has lone pairs, is basic. It has a lone pair that's not part of the pi system. Brian?
Does basicity play any role in stability, or are they totally unrelated? Like, is a basic molecule not stable and oxygen, for example?
I don't know that I would make the connection that way. The way I would make the connection is this, that the oxygen is basic. I wouldn't make a connection in that case. I would say the oxygen's basic and the molecule's aromatic. For the two nitrogens, for pyridine and pyrrole, the nitrogen is either basic or non-basic depending on the structure of the molecule. So the structure lends itself to the nitrogen either being basic or not basic. And so I would look at it more that way. Is that nitrogen basic? It either is or isn't, depending on whether the lone pair contributes to the aromaticity, and if it does, then that makes the molecules more stable. Sarah?
So for a pair of electrons, can it have the choice between not being part of the pi system to make it sp3 instead of sp2, or is it always going to be these scenarios?
If it has a choice to become part of the aromatic system and become aromatic, it's going to.
Okay.
The molecules are always going to go to their most stable energy, or go to the lowest energy. So if the nitrogen's like, well, I'm going to buck the system and I'm going to hold my pair of electrons out of the pi system, that's not going to work.
Okay.
It doesn't have that choice. It's got to contribute if it becomes aromatic. Now, if it has a choice of contributing and becoming anti-aromatic, it won't, because it doesn't want to become unstable.
Mm-hmm.
But if it makes it more stable, that's what it's going to do.
Sorry, can you explain just one more time what happens to the hydrogen in pyrrole, since those electrons are only part of the pi system?
It's just the hydrogen is bonded to one of the hybrid orbitals, one of the sp2 hybrid orbitals, and so it's outside the system. And it's not that, it's we're saying if I had an H plus, would the nitrogen bond the H plus? And it can't, because its pair of electrons are already spoken for in the ring. Whereas down here, the oxygen now has a lone pair outside of the pi system that it can use to bond the H plus and still become aromatic. What?
So is it basic or no?
It is basic.
It is basic.
Yes.
Is it
Any,
involved at all? It's basic.
if it's involved in the pi system, if all of its electrons are involved in the pi system, it's not basic. If it has a pair of electrons outside of the pi system, then it will be basic, because it will be able to bond an H plus.
Confused with like how you tell the electrons are part of the system.
That's where you have to basically take the molecule and decide whether it's aromatic or not first. So let's see. We can do this, the thiophene, because it's sulfur and not, it's a sulfur, which is a new atom. So if I said, is that sulfur basic? It means, is that sulfur able to use one of those two lone pairs to bond an H plus? So the first thing I'd have to ask is, well, actually I wouldn't even have to, I'd just go, it has two pairs. Whether one of those can contribute, one of those could contribute or not contribute, I'm still going to have one left over to the pi system to make it aromatic. But let's say it's not. Let's say I say, is this aromatic or not? I've got 2, 4 pi electrons. I'm looking for 6. What I'm looking for is this to contribute to. The first way it contributes to is it's sp2 hybridized. So if that sulfur is sp2 hybridized, then that sulfur will look like this. It will have a p orbital, and it will have a bond that way. Right? And then over here we've got the double bond, and then the other double bond. So for the sulfur to become sp2 hybridized, or the only way it can contribute to is if it's sp2 hybridized. The sulfur does that, says I'm going to put my 2 electrons there, I'm going to put my 2 electrons here. Now these 2 electrons are part of the pi system. I've got 2, 4, 6. System's aromatic. Does the sulfur have a lone pair outside of that? The answer is yes. And so it could bond an H plus. So you have to determine whether it'll go sp2 or stay sp3 as part of determining whether the molecule's aromatic, and then determining where the electrons are after it becomes aromatic. And if it can't, doesn't matter, because then it didn't use those lone pairs. It can take all the protons it wants, up to 1. So the first thing is, what's the structure of the molecule, and then does it have lone pairs outside the system to be able to bond? What else?
Logistics. Is the next lecture, is that just going to be the second half of this packet? So I was uploaded, but I didn't click on it.
I think so. I think if there's extra slides left over, that's where I start. That's up in the folder already for Wednesday. I think it's the beginning of, because we had side chain reactions in this video, right? It'll start with side chain reactions, and then it'll go.
Production.
That's not really a side chain reaction, but
Well, that's the first thing.
right,
Right.
yeah. That and side chains.
You want to give a preview of it?
No. You don't need to hear it twice. Everybody okay? Well, so let me just go back for a minute. So you might ask, well, what is a superstability? How does that manifest itself? And let's use the example of the cyclopentadiene as the example. Now, I want to deprotonate this hydrogen, right? I want to deprotonate that hydrogen to make a C minus. So what kind of base should I use? H2 minus? Will NH2 minus deprotonate that? Well, I didn't say whether you were right or wrong. How do we deprotonate a carbon to make a C minus? What base do we use? H minus maybe. But what's the problem with trying to take a carbon-hydrogen bond and deprotonate it to make a C minus? I need a base that's stronger than C minus, right? Which is what? No, in my periodic table it goes CNOF. So what's the strongest base there? Is it C minus or F minus? C minus. So the strongest there is C minus. I mean, you could make the argument H minus maybe. But usually C and H we consider to have about the same basicity. So how do I deprotonate an alkane to make a C minus? And the answer is, if this carbon is an alkane or an alkene, that's not happening. I can't just simply deprotonate the CH bond and make a C minus, which is good for Victor Grignard, because then by finding a way to make a C minus, he and the rest of the people he built his reaction on won the Nobel Prize. Although actually no people made C minuses before Grignard, but they didn't get the Nobel Prize. I think Barbier did that earlier on. But that's the only way we can make a C minus. I can't just deprotonate. Well, wait, that's not true, is it? Because I seem to remember doing something like this. And making an alkynyl anion. Right? Do you remember doing that? So, you might be able to deprotonate an sp carbon hydrogen, but that's about it. An sp2 hybridized carbon is going to be really difficult to deprotonate, but not for cyclopentadiene. For cyclopentadiene, I can use NH2 minus. I can use hydroxide. I can use an alkoxide. I might even be able to use bicarbonate, although I wouldn't. Sure, any alkoxide. So I could use H minus, I could use an NH2 minus, I could use any kind of O minus to deprotonate that hydrogen on the cyclopentadiene. It's really easy to do. And then I'd ask you why in some sort of essay question and say, why does that work? And we would think about this being acid-base equilibrium. Right? So I've got my cyclopentadiene, and I've got an acid-base equilibrium where I form my anion and my H+. So it turns out that the hydrogens of the cyclopentadiene are pretty acidic. If I can use weaker bases to deprotonate them, that means they're stronger acids. So I might ask you, why is the hydrogen on the cyclopentadiene more acidic than your run-of-the-mill alkane? Or better yet, why is it more acidic than any other allylic hydrogen? And you would say,
when you remove it gives an extra pair of electrons, so then it makes the ring an aromatic, and because the electrons will go into the empty p orbital.
okay, electrons will go into the empty p orbital, and then the molecule will become more stable.
And aromatic.
Aromatic, so it's really stable. Okay? That's relevant to what we're doing today. So what does that do to the equilibrium? To?
Right.
Okay, it shifts the equilibrium to the right. Because what have I done to the conjugate base? I've made it more stable. Have we ever used that principle before? The answer is yes. I wouldn't ask if we hadn't. Right? When we're talking about acidity, anything I can do to stabilize the conjugate base is going to make the resulting acid more acidic. So making this aromatic means that those hydrogens can be removed by very relatively weak bases. So it doesn't take anything to remove those hydrogens and make the cyclopentadiene, the cyclopentadienyl anion. So I think hydroxide would do that. Right? Hydroxide removing a CH bond? Well, only if you're going to make something that's really stable, like an aromatic anion. Now, I could still add acid back and get back my cyclopentadiene, but these things, when you write them, you'll see these written with the negative charge on the inside with the circle. What people first did with these, I think this is another Nobel Prize, is they made sandwiches out of them. They made iron sandwiches, so the two anions, the two negative charges, will sit above and below at Fe2+. To make the molecule called ferrocene. That's inorganic chemistry because we're using metals, but that's what they're used for. So how do I know that there is this thing, this superstability? Because it manifests itself in that property. If I took this chloride and I took that chloride, and I reacted them with water, which one reacts faster? Top one? We all agreed it's the top one? Why? Because what kind of mechanism is this? SN1, so I'm going to form 2 carbocations. That one versus that one. But the bottom one's not bad. That's allylic. But the one on top, it's not just that it has more resonance. It's more stable because it's aromatic. Okay. So one of those carbocations is not aromatic, and one of them is. And so then we go back to last semester and we say, well, what's giving us the rate of an SN1 mechanism? The rate determining step, which is the formation of the carbocation. So then we go back and we revisit Hammond's postulate, which means if this is my reactant and this is my intermediate, what did I just do? I lowered the energy of the intermediate by a lot. So what happened to the activation energy? It went down too, which means they're formed faster because the activation energy is smaller. Brian?
So if you finish that reaction for the aromatic ion, you would have an OH and an H on that. That make it sp3 hybridized, and that breaks the aromaticity.
Yes. But remember, it's a positive charge.
So that it's willing to become non-aromatic to get rid of that positive charge. Okay.
2 totally different situations here. Aromatic carbocations are super stable, but they're still carbocations. They're still short an electron, so they will react. Right? I mean, you can put carbocations in a bottle, but not forever. You know, eventually they will react with something. I mean, there's maybe radicals that you can put in a bottle and they'll stay as a radical forever. That's not even true. But there's radicals that'll persist. So yeah, it doesn't have a choice. It would love to get back to neutral. But as far as this reaction goes, if I did that, measured the rates of those 2 reactions, aromaticity is real. And so that top reaction would go a lot faster than the bottom one. Okay. Aaron?
Which final product will be most stable? Is it just the secondary?
Well, so the cyclopropyl alkene has some issues. It's got a lot of issues. Because I'm trying to bend a 120 degree bond into a 60 degree bond, and it's not happy about that. But that's where if I was going to look at this and look at these 2 reactions first, the first thing I do is I go to the lab and I measure their rates, and I see what the trend is. And if the trend is that the top one's faster than the bottom one, then I'm likely to say that the aromaticity, that the reduction in transition state energy, has beaten anything we get on the other side with stability of product. Because you can imagine that we have a situation where we've got starting out with molecules that are roughly the same energy, which these 2 are not. See, normally we talk about starting with molecules that are the same, but they got to go over and down. So the reaction that's going to occur fastest is going to be the one with the lower transition state energy. But in order for us to do that, I need to know the energy difference in the molecules on the left and I need to know the transition state energy. So there are limits to Hammond's postulate. And one of the limits is that we always start with molecules same energy. If they're different, I can't do that. So that's one of the fundamental misuses of Hammond's postulate, which I probably just did there. But nobody cares because it's time to go. All right, does that kind of make sense? So here's I've got problems up here for you to do. So, but we'll start in class on, oh, that's right, today's Wednesday. We'll start with that molecule, and I will ask you, is that aromatic, non-aromatic, or anti-aromatic? Because that's one of my favorites that's not on the quiz. Okay? All right, so then you can turn in your problems for today. Take those problems. Oh, that's right, I got exams. The exam key is posted. I haven't put your scores in the computer yet. I will do that. So you're better to come to me to get these. Brian. Take one. UK one.
Thank you.
Madison. Haley. Carolyn. I didn't see her back there.
You gave it to us in class.
Erica. Marissa. Kyle. Maddie. Josh. Reem. Kate. Christian. Aaron. Vinny.
Just like turn it off and then we're trying to reset.
Shereen.
So I don't miss Diane. No, mine went.
Rhea.
Oh, I don't know. Well, I think we're going to go back. So.
Nelly. She must have gone somewhere far, far away. I guess when you need to take information,
I had my homework that was due last week. I just put it in the bed.
Thank you.
Yeah.
Is this out of 207?
yeah. Well, no, actually, it's 200. But that's not a big curve. Because we don't curve until the end. Go through it, see what you missed.
Yep.
Get back, get that stuff under control. Keep this stuff under control.
I missed where we got.